Today we are going to discuss algebra of functions as well as function composition. So if f and g are any two functions, we can add, subtract, multiply, or divide them just like the way we can do two polynomials. The domain of new function will be all x values that satisfy the domain of both f of x and g of x. If new function involves division, the domain must not include any x values that make the g of x function undefined. That makes the denominator 0. So we'll be looking at addition function, subtraction function, multiplication function, as well as division function, and discussing their domains as well. So here's an example. We're going to be finding all four functions given f of x and g of x. So to find the addition function, we're just going to go ahead and add the two polynomials. And that's going to be x squared plus 3x minus 6. And domain will be negative infinity to positive infinity, all real numbers, because this function is defined everywhere. F minus g of x, x squared plus 2x minus 1. Be extra careful. We're going to be subtracting the binomial, so make sure to put parentheses around. X squared plus 2x minus 1 minus x plus 5. So subtraction function turns out to be x squared plus x plus 4. And again, domain will be negative infinity to infinity. Next, we're going to be talking about product function, f times g of x. For product function, we can simply go ahead and multiply the two functions, and we would be using distributive property to multiply them. So we can do this and then combine the like terms. So it would be x to the third minus 5x squared plus 2x to the second power minus 10x minus x plus 5. Combining the like terms, we get x to the third minus 3x squared minus 11x plus 5. And domain, again, will be all real numbers from negative infinity to positive infinity. The fourth function we're going to look at is the division function. For division function, we have to be extra careful about the domain, because the domain of new function has to satisfy both individual functions. And if we have a denominator, we want to make sure the denominator does not equal 0. F over gx would be x squared plus 2x minus 1 over x minus 5. And as long as x is not equal to 5, that's okay. So our domain in this case would be negative infinity to 5, union 5 to infinity. Other than 5, every other x value is allowed. Every other x value will give us a real output value. Now, pause for a minute. Go ahead and try finding addition, subtraction, multiplication, and division function when we're given f of x and g of x. Come back and check your work. Addition function, its domain. Subtraction function, its domain. Multiplication function, its domain. And division function as well as its domain. Be careful with the domain of division function. We don't want denominator to equal 0. Okay. Any values that make g of x equal to 0 should be excluded from f over g of x. Now in this case, our division function does not have a denominator. There's no factors in the denominator. We still want to make sure we don't include any x value that makes g of x 0, because our function is going to have a discontinuity. There is going to be a hole at that point, x equals negative 9. composition of functions is denoted by f of g of x. F of gx or fog x. So FOGX is same thing as f of gx. So composition means we are replacing the x by a new x, which is g of x. The domain of the composite function f of g is the set of all x in the domain of g such that g of x is in the domain of f. So we have to exclude any values that are not in the domain of g, and then we also have to exclude any values that are not in the domain of f of gx function. So x must be in the domain of g and g of x must be in the domain of f of gx. Then we can have, that would be the domain of f of gx. Let's see some examples. Find each composite function, determine the domain of each composite function. So we're given f of x and g of x. We want to find the composition and we want to find the domain of it. So composition f of gx can be found by replacing the x inside the f function by the new x. So the new x is going to be x plus 1 now. What is f of x plus 1 going to equal? What's the rule of f function? Any input values that goes in to the f function multiplies it by 2 and subtracts a 3 from it. So now my new input value that's going in is x plus 1. F function is going to multiply this input value by 2 and subtract a 3 from it, which is going to be 2x plus 2 minus 3, and that's 2x minus 1. So f of gx is 2x minus 1. Now what's the domain of this f of gx? Well, domain is all the values of x such that x is in the domain of g and g of x is in the domain of f of g. Now here both of these functions are linear functions. There's no domain restrictions. So domain in this case would be all real numbers, negative infinity to positive infinity. Another example. In this case, we are given the f of x, we are given the g of x, we're looking for g of f of x, and we want to find the domain of the composite function. G of f of x is g of f of x. So g of the new x inside the g function will be the f of x, which is x minus 3. What is the rule of g function? What does g function do to an input that goes in? Whatever input goes in, g function squares it and adds a 1 to it. So g function is going to square x minus 3 and add a 1 to it. Now we can go ahead and simplify this by foiling, and that would be x squared minus 6x plus 9 plus 1, which is x squared minus 6x plus 10. Now domain in this case is going to be, domain of g of f function is all the x values that are in domain of f such that f of x is in the domain of g of f. Okay, so again, in this case, both functions are linear and we don't have any divisions, we don't have any fractions involved, no logarithmic functions involved, no radicals involved. So domain is going to be all real numbers in this case again. Let's see another example. Find the composite function, determine the domain of composite function. Now we got to be a little careful with the domain because we have fractions involved here. So first of all, let's go ahead and find composite function f of gx. F of gx is going to be f of gx. Inside my f function, the new x is going to be g of x, which is 1 over x. Now, what does f function do to something? What does f function do to any input that goes inside? It makes it 2 over that input minus 3. So 2 over that input minus 3. Let's go ahead and simplify it. We have a complex fraction here, 1 minus 3x, and that's going to turn out to be, that's going to be not a 3 in the denominator. It's going to be an x in the denominator, 1 minus 3x. That would be 2x over 1 minus 3x. So that's my composition function f of gx, 2x over 1 minus 3x. Now domain is going to be all the values in the domain of g such that g of x is in the domain of f of gx. So what are the allowed values for the domain of g? For g function, the allowed values are everything is okay other than 0, because other than 0, all the other x values are allowed because 0 makes the function undefined. Now, f of g function is 2x over 1 minus 3x. And what is the not allowed x value here? That would be x cannot equal 1/3. So domain of f of g function in this case will be, we have to exclude x cannot equal 0, x cannot equal 1/3. Other than that, all real numbers. So negative infinity to 0, union 0 to 1/3, union 1/3 to infinity. It's a tried problem. Let's see. F of x and g of x are given. We're looking for g of f of x. Okay, so in this case, g of f of x, which is going to be 2 over x. What does g function do to any input that goes inside? It flips it, writes the reciprocal of it. So that's going to be g of 2 over x will be 1 over 2 over x, and that's going to be x over 2. What would be domain for this function? So all values that are in the domain of inner function, as long as they also don't make g of f undefined. So for this one, we are okay with our g of f function is g of f function is 2 over x over 2. And all the values in the domain of inner function in this case was, we found g of fx, so the inner function was 2 over x. And all the values that are in the domain of 2 over x are other than 0. It's going to be domain of f now, f. So other than 0, all the values are allowed, and all these values are also okay with g of fx because they don't make it undefined. So our domain for g of fx is going to be negative infinity to 0, union 0 to infinity. We will be excluding the 0 from the domain. Find and then evaluate each composite function. So here we have to find f of g of 6. We can do it in two different ways. We can find f of gx and then replace the x by 6, which is going to be f of g of x. F of g of x is x minus 2, and that would be square root of x minus 2. Now we can go ahead and replace x by 6. F of g of 6 will be replace x by 6. Square root of 4 is 2. The other way we could handle this problem is we could find f of g of 6. So what's g of 6? Let's find g of 6. The function g of x is x minus 2. G of 6 is 6 minus 2, which is 4. So f of 4 is square root of 4, which is 2. So we could do it in either way. Usually it's easier to do the second way when your functions are more complicated. Another example, we want to find g of f of 2. If you are not just finding g of f of x, but you're looking at a particular value of x, it's a lot easier to do g of f of 2. Now let's find f of 2 first. F of x is 6x minus 1. F of 2 will be 6 times 2 minus 1, which is 12 minus 1, which is 11. So we are finding g of 11. And g function will add a 3 to the input and divide by 2. 11 plus 3 is 14 divided by 2 is 7. So g of f of 2 is 7. We could also do it the longer way. We could find g of f of x and simplify it, and then finally replace the x by 2, and that would also give us the same answer. Decomposition of composite function. Decomposing means breaking it into the pieces that were used to make the composite function. A lot of times there's more than one possible answer to more than one possible way to decompose a function, but sometimes one comes easier to the mind than the other option. Here's an example. Express the given function. H of x is actually a composite function. H of x is a composite function. We are given a composite function, and we are looking for what two functions were composed to give us this new function. We are going to be finding f of x and g of x. Again, there can be more than one possible answer, but sometimes one answer is easier than the other. Here, I think if f of x was x squared and g of x is x cubed minus 3x, if we compose these two functions, we would get this function. You can check by doing f of gx. That would be f of, and that's going to give us x to the third. So that's going to be our h of x function. So in this case, we can say our two functions that were used to get this new function, composite function, f of x is x squared, g of x is x to the third minus 3x. You cannot reverse the order. You cannot switch f of x and g of x because that would not give you the same composite function if you switch which function is f of x and which function is g of x. Let's see another example. H of x is 3 over 3x minus 5. F of x, we could use 3 over x minus 5, and g of x could have been 3x, or the other possibility, f of x could have been 3 over x, and g of x could have been 3x minus 5. Again, if you compose and you find f of gx, it's going to be 3 over 3x minus 5. Same with the second set of functions. So there's multiple possible answers. Sometimes one is easier to think or guess than the other possible options. That's all for composition of functions and algebra on functions.